This video is on part 2 of section 4.4. This is part 2 of section 4.4, and it's about finding holes along with vertical asymptotes. So let's take this problem, x squared plus 3x plus 2 over x squared minus 4. Now, in order to work with this, to find vertical asymptotes, I really need to factor the bottom. So I'm going to make that x plus 2 times x minus 2. If you're not sure how to factor, go back and find some videos on factoring quadratics. And the top is going to be x plus 2 times x plus 1. Now, I know that you can see that x plus 2 would factor out. And that's going to create what we call a hole. Think about it. When you dig a hole, you remove the dirt, and it leaves a hole behind. By removing these factors, it created a hole. Well, where did that hole exist? It existed when x plus 2 equals 0, so the hole exists at x equals negative 2. And we would make sure to keep that information for when we're graphing, that at negative 2, there is going to exist a hole in my graph. But there's still a factor that didn't get marked out in the denominator. Remember in our last video, I told you that you're looking for denominator restrictions to tell you where the vertical asymptotes are. This was a hole. This one is going to create a vertical asymptote. So x minus 2 equals 0, x equals 2 means that there is a vertical asymptote at x equals 2. Let's try one more, and I'm going to give you this one already in factored form so that we don't have to take time for that. Let's say that I had x plus 3 times x minus 3 over x plus 1 times x minus 3. Do you see the factor that can be removed that's going to create a hole? That hole will exist when x minus 3 is 0, so x equals 3. That will be a hole. The one that isn't removed, x plus 1 equals 0, so x equals negative 1. It's a restriction for our domain. In my domain, I would say x can't be negative 1, but it can be every other number. But for vertical asymptote, I'm going to say x equals negative 1. Okay? Just boxing in my answers so they're easy to find. The next type of asymptote that we're going to find is a horizontal asymptote. Horizontal asymptotes are horizontal lines. And on a graph, what happens is when we draw a horizontal asymptote, let me just draw one right here. Let's draw horizontal asymptote, okay? Whenever we're drawing the graph, there can be a whole bunch of stuff that's going on in the middle here. It doesn't really matter. But what a horizontal asymptote tells me is that as the graph moves out further, it's going to look closer and closer like my green line. It would eventually not be able to tell the difference between my graph and the green line the farther out you go. That's what a horizontal asymptote is. But I want you to see something. Do you notice that I crossed that horizontal asymptote all over the place? That's allowed. If I want to cross a horizontal asymptote, sometimes the values do cross. Sometimes you're going to see graphs where the asymptote, the horizontal asymptote, does cross. So how am I supposed to know where it's going to be? Well, this is found by looking at the degree of the numerator compared to the degree of the denominator. Okay? We're going to compare the degree of the numerator with the degree of the denominator. Let me show you what I'm talking about. Let's go back to this problem right here. I have f of x equals x minus 1 over x squared plus 5x plus 4. Well, the degree of my numerator is 1. That's because it has the highest exponent is 1 when it's all in simplified form. The degree of my denominator is 2. When I'm comparing that, this is the bigger degree. In other words, it's bigger on the bottom. Now, some of you, when years past, heard of something called BOBO. Bobotn. B-O-B-O-B-O-B-N. B-O-T-N. Bobotn. Okay? Well, what that stood for was if it's bigger on the bottom, you're going to get 0. So for this problem, y equals 0 is the horizontal asymptote. By the way, horizontal asymptotes are always written as y equals some number. Okay? They're always written as y equals some number. So this would be y equals 0 because it's bigger on the bottom and therefore it's 0. Well, if it's bigger on the top, which is what botn stood for, we used to say bigger on the top, there is none. And that's true, there is no horizontal asymptote. But what if it was bigger on the top now, and we're in this class, they ask us about something called oblique asymptotes. And we'll get to that in a minute. Just don't forget, we're going to come back to oblique asymptotes. But there's one case that isn't discussed in Bobotn, and that's when the degree is the same. Let me show you an example of that. Let's say that I took g of x is equal to 3x squared plus 3x minus 2 over x squared minus 4. Well, the degree on the top is 2. The degree on the bottom is 2. So these are the same degree. Now, the coefficients are different, but the degree is the same, and that's all that matters here. Whenever the degree is the same, you look at the leading coefficients, 3 on top and 1 on the bottom, and you divide them. So if I took 3 divided by 1 equals y, then y equals 3 is the horizontal asymptote. So here it was y equals 0 because it was bigger on the bottom. Here it's y equals 3 because when it's the same, you divide the leading coefficients. Let's do a few more practice problems with that. Okay, let's take r of x is equal to x minus 12 over 4x squared plus x plus 1. The degree of the numerator is 1. The degree of the denominator is 2. This is bigger on the bottom. Bigger on bottom, Bobo. So y equals 0. Let's try another one. R of x, so in other words, rational function of x, is equal to 8x squared minus x plus 2 over 4x squared minus 1. Well, what's the degree? It's a degree of 2 over degree of 2, so these are the same. So where do I look? Leading coefficients. And I'm going to divide those leading coefficients. And it's going to be y equals 8 divided by 4, so y equals 2 is my horizontal asymptote. Okay, this one was y equals 0, this one is y equals 2. Now let's get back to what we were talking about before with oblique asymptotes. Oblique asymptotes are slant asymptotes. They are slant. And on a graph, what they look like is like this. And my graph might end up looking where it's climbing through here and it approaches that asymptote. It's approaching through here and it approaches that asymptote. And it might do some weird stuff in the middle, but the ends, it's going to approach that asymptote right here, right? It's going to act like that particular line. So how do we find that? Well, let's take a look at this problem. 3x to the 4th minus x squared divided by x cubed minus x squared plus 1. I'm going to leave it to you to do the long division, but you need to know that once we do long division, we're going to find out that 3x is the linear behavior of my graph. It's actually going to act like 3x, and that would give me the oblique asymptote. Y equals 3x when you divide that, okay? So let me finish. I forgot that it was plus 3 because it goes 3 more times.